Glad you're all here together after spring break. Good morning, Jason. Welcome back. We're getting started here on the warm-up. So in order to solve for x in this problem, we first need to subtract 1 from both sides so that we have that 3 to the x power by itself. It's 3 to the x now equals 81. And we might be able to look at this and guess and check what it is, what the answer is. But we could also rewrite this as log base 3 of 81 is equal to x. And then we could put that log base 3 of 81 into our calculators. Probably going to use the Desmos graphing calculator. And the answer would be 4, because here 3 to the 4th power equals 81. 3 squared is 9. 3 to the 3rd is 27. 3 to the 4th is 81. So x equals 4. On the next one here, similarly, we need to subtract 1 from both sides. We get log base 2 of x is equal to 3. And now we're going to rewrite this in exponential form so that it is 2 base 2 to the 3rd power equals x. And 2 times 2 is 4 times 2 is 8. So this is 8 is equal to x. On this one, our exponent has a variable in it, so we're going to have to convert to a logarithm form. Similarly here, the exponent has a variable in it. So converting to log form, we have log base 3 of 81 is equal to x plus 1. So notice that my entire exponent is equal to the logarithm. And log base 3 of 81, well, we already saw that log base 3 of 81 is equal to 4. So this is 4 is equal to x plus 1. Subtracting 1 from both sides to isolate the x. And we have 3 is equal to x. On this one, our variable is in the argument of the logarithm, so we have to convert to an exponential form. So we have 3 to the 4th power is equal to x plus 1. And 3 to the 4th power, well, we already saw that 3 to the 4th power is 81. So this is 81 is equal to x plus 1. Subtracting 1 from both sides, and we get 80 is equal to x. Good morning, Elizabeth. Glad you're here with us. Are there questions on any of those warm-up problems? If you're doing these, watching this video at home, have a look at these, maybe pause the video and try to remember what the answers are going to be here, and then I'll go through them. So when you're multiplying the same base x to some exponents, 5 and 3 here, then what you do is you can rewrite this as x to the 5 plus 3, or x to the 8th power. So you have to have the same bases, multiplying them, and you then combine them together where you add the exponents, all right? And so in this one, that's the same rule. So it's going to be x to the 2 plus 7, which is x to the 9th. On this one, really, you can think of this as, because we're raising this to the third power, you can really think of this as x to the 5th times x to the 5th times x to the 5th. And now, since we're multiplying these things that have the same base to some, and they have powers, you can think of it as adding those together, x to the 5 plus 5 plus 5, which is x to the 15th. However, it's a little quicker just to take this 3 and multiply it by the 5 to get the 15. So that's when you have a base raised to a power, and then that whole thing is raised to some other power. You multiply the exponents there. So in this one, same idea. It would be x squared times x squared multiplying itself 7 times, or just take that 7, multiply by the 2, and you get x to the 14th. Now here, well, no, let's look at this one, sorry. Here, we're multiplying these two bases to powers, but they're the same bases, and we add the exponents, 5 and 3. In this one, we're dividing the same bases raised to some powers. So you can really think of it as subtracting, but if you think about this, what you have is x times x times x times x times x over x times x times x. And these make a 1, those make a 1, those make a 1, and so you get x squared. And really, so it's x to the 5 minus 3. So you take the same bases, combine them into one base, take the numerator exponent, subtract the denominator exponent, and that's what you get right there. Now on this one, x squared over x to the 7th is going to be x to the 2 minus 7, which is x to the negative 5, which is 1 over x to the 5th. So we don't usually leave our exponents as negatives there, so we would rewrite that as 1 over x to the 5th. Questions on any of those? Hopefully that's just a refresher as we look a little bit closer at these. Can someone use one of the exponential laws to tell me why this makes sense? Whenever you have some number raised to the 0 power, the result is 1. It doesn't matter what the value of x is. What law could you use there? Well, let's just pick any number y. X to the 0 is equal to x to the y minus y. So this is looking at this rule where we went from a fraction with the bases that are the same bases raised to some powers, and we're subtracting them. So the result here was 2. So what we're doing is we're working backwards. So if we were given this, we could write it like that and then write it like that. So when we're given x to the 0, we could rewrite it as x to the some number minus that same number, because y minus y equals 0. But now we can rewrite this as x to the y over x to the y, because whenever you're subtracting two exponents, you could rewrite it as the same bases. This y is right there, this y is right there. But whenever we have some number x to the y over some number x to the y, because the numerator and the denominator are the same, it equals 1. And so this explanation is why this must always be true. So we could look at an example like 3 to the 0. Well, that equals 3 to the, we can pick any number for y, 3 to the 4 minus 4, which is equal to 3 to the 4th over 3 to the 4th. Well, we know this is 81. We know this is 81. So that has to equal 1. So this is just an example where x is 3 and y here is the 4. Questions on that one? All right. This one builds off of what we see right there. Okay? And here's why. No matter what our a value is here, no matter what our a value is, if it's x to the negative a, any number to a negative exponent, we can think of that as x to the 0 minus a. Instead of just saying negative a, we can call that 0 minus a. Well, then we can break this apart, just like we broke this apart. X to the 0 over x to the a. Well, we just saw that anything to the 0 power is 1. So this, x to the 0, is 1 over x to the a. So this is my explanation for why this is true. Questions on that one? This next one, this is a square root. Sorry, it didn't look like it. So this is saying, all right, x to the 0.5 is equal to square root x. And you may think to yourself, wait a second, why would that be true? X to the 0.5 is equal to square root x. Well, let's think about it. What is x to the 0.5? Well, that's really x to the 1/2. So x to the 0.5 is equal to x to the 1/2. And that is true because we have not sure how Mr. Maurer wanted me to think about this. Well, this is the way that the basic idea works. Whenever we have a fraction as an exponent, the numerator of the fraction stays attached to our base. So it's like x to the first power. And the denominator of our fraction that is in the exponent becomes the root of the base. So x to the 1/2 becomes square root, because this is a denominator of 2, x to the first, because this is a 1 right there. So the more general rule here is x to the a over b is equal to root b of x to the a. That's the more general rule. This looks a little like a 9. Let me fix that. Okay. Any questions on that one? I hope you're taking notes. Okay. All right. So here, these are the logarithmic rules. So notice that here we have log base 2 of x plus log base 2 of y. It's essential here that our bases are the same. Otherwise, it's not an application of the rule. Does anyone have an idea what this will equal? Remember that. Remember that here is the rule for exponents. Well, this equals log base 2 of x times y. And so we can go this way, but we can also go that way. Often you see breaking it apart. Sometimes you see combining it together. It goes both ways. Both ways are important. On this one, notice we have log base 5 of x to the third power. So really here, I'm gonna zoom in here for just a moment. It's important to know that this is the argument is x to the third. It's not this. Those are two different things. So this way, we're raising log base 5 of x, all of that to the third power. This way, we're just raising x to the third power. Okay. So now, given that, if we look at this rule right here, it's probably a little harder to see on this one. But it's going to be, we take that exponent here, and it moves out to the front. So that becomes 3 times log base 5 of x. 3 times log base 5 of x. Questions on that one? That's called the logarithmic power rule. Hey, David, good morning. Good to see you here. All right. So this next one, it relies on this rule. It's related to that rule. So again, it's essential that you have the same bases there. Doesn't matter what they are, just as long as they are the same. So in this one, we have log base 3. So we are subtracting these two logarithms. The argument of the first logarithm becomes the numerator, and the argument of the second logarithm becomes the denominator, in the argument of the new one, of the new logarithm. Okay. So notice we're subtracting two logarithms, and here the result is the argument becomes the one base, or excuse me, one argument divided by another. Here, we're subtracting two exponents and then we split them apart in a division. So they're related here in really important ways. I should say questions on that one before we move on. So before you get away from me today, we're going to go through a couple practice problems here. I'm going to zoom in on this first one. In order to isolate our x, it's in an exponent, so that means we're going to need to use a logarithm eventually. But first, we need to subtract 1 from both sides. So we get 2 times 3 to the x power is equal to 162. Now, since this is multiplication, the inverse operation of multiplication is division. So now we have 3 to the x is equal to, well, 162 divided by 2 is 81. And you may look at that and remember what the answer here is, just from the warm-up. But we can rewrite this as a logarithm. Log base 3 of 81 is equal to x. And if you use your calculator, you will find that log base 3 of 81 is 4. So our answer here is 4. Questions on that first problem? All right. Does anyone have an idea where to start with this one? Where should I start? Well, notice that we have 2 log base 2's. We're subtracting them. So which rule can we use? Well, we're going to get a log base 2. Yes, Ham, no, you're exactly right. So we have that x plus 5 divided by x. That's exactly right. And that equals 1. And I'm not going to lie, that looks terrible. That's hard, right? Well, let's work with it and see if it really is. So now the argument of our logarithm has some variables in it. Since our logarithm is base 2, we can rewrite this 2. And then remember, whatever the logarithm is equal to, 1, that's our exponent. So this is 1. And that equals x plus 5 over x. Still looks pretty rough, right? Well, 2 to the first power, that's just 2. But how do we deal with this? Does anybody have an idea of what we can do there? I think hmm, the easiest thing to do is probably to multiply through by x. So I'm going to go like this and say times x. Well, that doesn't look like it's going to work, does it? Because if we multiply through by x, we're just going to end up with the same kind of situation. So instead, maybe what we need to do is to break this apart into 2 fractions. X over x plus 5 over x. Now we're getting somewhere. The reason why that was valuable is because x over x is just 1. So we have 2 equals 1 plus 5 over x. This was tricky, really tricky. Now we're going to subtract 1 from both sides, and we get 1 is equal to 5 over x. Now, if we multiply both sides by x, we get x equals 5. Whew. Tricky steps. So going from this step to that step, I think is tricky. Remembering that you can break a fraction apart like that. And then it might have been, you might not have seen that that was going to change x over x was 1, so you might not have thought to do that. That's tough. Any questions on that one? Okay, so things I want you to do. First, I want you to work on that. I'm gonna stop the video here.